Now on to chapter 16 on oxidation and reduction. So, right now, the primary fuel of the cars, at least here in the United States, is gasoline. What's going to fuel them? So, we have a couple ideas. Of course, we can go electrical cars, but there is another option. You can use fuel cells. And a fuel cell uses, well, the fuel cells that we have now, we have them that can run off of hydrogen and oxygen, and we've had them for a while. We first started using them in the 1960s because fuel cells was what powered spacecraft, and then the water byproduct would be used to give to the astronauts to drink. But it is something, it's also very efficient. Internal combustion engines are not terribly efficient. So fuel cells are much more efficient, on the order of 60%, whereas a gasoline powered car is about 20% efficient. So it just depends. We're working on getting them better. Problem is, fuel cells are very expensive. So it's on, well, we're going to talk about oxidation reduction. It has to deal with this type, the oxidation reduction, the fact that some elements give electrons to other elements, and then as the electrons move, we can use them to do work. And in this case, hydrogen gives its electrons to oxygen. And this is an exothermic reaction. And with the energy coming from the electrons, the electromotive force of that we can then use to run a motor. So oxygen is the one that is getting the electrons. So we'll talk about this soon. Oxygen is getting reduced. It is the oxidizing agent. It's causing hydrogen to become oxidized, and that means also then hydrogen is the reducing agent. So fuels are the most common reducing agents. Oxygen is the most common oxidizing agent. So we'll talk about this. So and we separate them, and actually it's a pretty complicated process, but they involves the hydrogen taking electrons, like it absorbs on the metal surface, and then the electrons leave the hydrogen. They go through the circuit and then go to the oxygen, and then reduces the oxygen. Then the hydrogen ions transport across to the oxygen to then form water. So you can see this is kind of a difficult process. So fuel cell technology is not an easy thing to do. But we'll talk about that near the end of the class, or this chapter, I should say. Let's talk about oxidation. Oxidation, well, the most general thing originally was you gain oxygen. So when things are oxidized, it gets more oxygen. It also loses hydrogen, so taking hydrogen away from compounds, especially if you study organic chemistry. And then, of course, the most general rule is losing electrons. So you can see here rust here, the iron is being oxidized, it's gaining oxygen, and also fire. Definition of fire is a rapid oxidation reduction reaction. So that's the most general. Oxidation is loss of electrons, and then reduction then is gain of electrons. So reduction can also be described as a loss of oxygen. It can be described as a gain of hydrogen, and it can also be defined as a gain of electrons. So and if you haven't noticed, then if something loses electrons, something needs to gain electrons. So oxidation reduction comes together, and sometimes we even abbreviate to redox. So these reactions have to happen in tandem. They have to happen together. So with the water example, so hydrogen is the reducing agent, is being oxidized. Oxygen is the oxidizing agent, is being reduced. And in the transfer of electrons from hydrogen to oxygen, then water is formed. So here, and some students have trouble with this because it's kind of like the opposite. So whatever is reduced is the oxidizing agent, and whatever is being oxidized is a reducing agent. So think of it as the oxygen is the oxidizing agent. It's causing oxidation. How does it cause oxidation? By being reduced. So it's absorbing electrons. It's causing the oxidation, but it itself is being reduced. The opposite is then true for the reducing agent. It is causing reduction. How is it causing reduction? It's giving away electrons. And then by giving away electrons, it is being oxidized. So by how it's causing it. So hopefully that makes more sense. So here are some mnemonics. I honestly don't use these, but if it helps you, oil rig, oxidation is loss of electrons, reduction is gain. Leo the lion says grr, Leo grr, lose electrons, oxidations, gain electrons, reduction. So hopefully this helps you if my explanation did not. So another thing about oxidation states, we can use these for bookkeeping. And this is a way of figuring out where electrons are in a chemical reaction. So this helps us in keeping track of them and how it works for oxidation reduction reactions. And the oxidation state, this is a very important thing, actually. So if you look at chromium, for instance, chromium metal is not toxic. Chromium plus 3 oxidation state is not toxic. But then chromium plus 6 is really nasty stuff. It causes both acute and chronic damage to people. So the oxidation state is very important for things' chemical properties. So also don't confuse this with ionic charge unless it's a monatomic ion. Then it is exactly its charge. But this is certainly a way we can use to track to see where electrons are going. And like I mentioned before, it does affect the chemical properties of the elements and compounds. So here are the rules for oxidation states, and they are hierarchical, meaning rule 1 is more important than rule 2 and so on. The first one is any free element, its oxidation state is 0. So it doesn't matter if it's iron metal, that's a free element. If it's oxygen, O2 gas, it's 0. If it's ozone, O3, it's 0. Any free element that just has one type of atom, that oxidation state is 0. So oxidation state of a monatomic ion is equal to its charge. So monatomic ion, one atom ion equals its charge. Then rule number 3, the sum of oxidation states of all atoms in a neutral molecule or formula unit is 0. So if you sum them all up, and I'll show you some examples, this is equal to 0. For a polyatomic ion, so many atoms ions, is equal to the charge of the ion, the complete charge. For in compounds, group 1, alkali metals are +1. For group 2, alkaline earths, they're +2 in compounds. And then in other compounds, this is a hierarchy table, also higher up top. So fluorine tends to be -1 in compounds. Then hydrogen tends to be +1. Oxygen tends to be -2. Group 7A halogens tend to be -1. 6A oxygen family -2. 5A nitrogen family -3. So let's use these to identify what's being oxidized, what's being reduced in this chemical reaction. Calcium metal plus 2 waters makes calcium hydroxide, aqueous, and hydrogen gas. So first we're going to start off with the oxidation state. And the elements are the easiest ones, right? So calcium metal is 0, hydrogen is 0. Then we move on, look at hydrogen, the table in rule 5. Hydrogen tends to be +1, oxygen tends to be -2. That fits perfectly. Then the calcium hydroxide, so calcium is an alkaline earth, it's +2. Oxygen tends to be -2, hydrogen +1. And you can see that if you sum these all up, though, the charge does in fact equal 0 for all of these. If you the one that's the most difficult, of course, is calcium hydroxide. So +2 plus 2 times -2 plus 2 times +1. So +2 minus 4 plus 2, that equals 0. So looking at all those, they all sum up to 0. And if you look what's being oxidized and reduced, calcium goes from 0 to +2, means it loses 2 electrons, so it's being oxidized. Hydrogen going from +1 to 0, it's being reduced, which means that calcium, metal, calcium solid, that makes it the reducing agent, and it makes water the oxidizing agent. So with that. So you can look at this. I actually like doing these. I know I'm weird, but tin is 0, hydrogen's +1, nitrogen +5, oxygen -2. Other side of the equation for tin, this is +4, oxygen -2. Nitrogen in NO2 is +4, oxygen is -2. Water, hydrogen +1, oxygen -2. So you can go through and try that out. An application that we use this in is bleaching of hair. Very commonly, you can use hydrogen peroxide, And hydrogen peroxide absorbs carbon dioxide in the air, and then it reacts with melanin and gives you that kind of bleached look. But you might notice your hair feels a little differently when you do this because it can also react with cysteine in your hair. So you have the disulfide linkages. Hair is a protein called keratin. It has a lot of cysteine in it and has these disulfide groups, and they can be broken by this, and it makes the hair feel a little bit more different. So it also can just kind of break some of the skin along the hair. So it's this way I say it's bad for your hair. So let's go and talk about redox equations. And students hate this, by the way. So this is one of the more difficult things students find in the class is balancing these equations. And one of the reasons why they have a hard time with this is because you have to keep track of the electrons. And an easy way to do this is the half electrons. And you balance the half electrons individually, and then you add them together. So for instance here, look at this. You have aluminum reacting with silver to form aluminum, aluminum metal reacting with silver ion to form aluminum ion, and then silver metal. And if you look at this, you think, oh, it's already balanced. It's a 1:1 to 1 to 1 molar ratio, right? We should all be good, right? And wrong, because actually aluminum is generating 3 electrons and silver is consuming 1. So we actually need to balance out the electrons. So we've identified first aluminum is being oxidized and the silver ion is being reduced. So we have to separate those out. And now we have to look at the number of electrons. So the number of electrons, if you look at aluminum oxidizing generates 3 electrons, and silver being reduced consumes 1 electron. So we are not getting the same number of electrons. So now when we look at these, if the aluminum generates 3 electrons, then the silver needs to consume 3 electrons. So we actually need 3 times as much silver as we have aluminum. And now when we go through here, and you can see, and you add these chemical equations up, and you actually have a 1 to 3 molar ratio between the aluminum and the silver. And this is because the aluminum generates 3 electrons and the silver only consumes 1 electron. So this is now balanced. So you typically only have to do this in oxidation reduction reactions. You don't have to worry about this in general. Usually when you balance chemical equations, it's not going to be this complicated. But for redox reactions, you have to make sure that you're doing this. And notice that that everything is balanced now in terms of number of atom and also number of electrons transferred. So and balance the charges, and you notice that we are have all of the charges balanced, all of the atoms balanced, and so on. So how do we do this? First thing is I assign oxidation states, and then look at the 2 half reactions. So see where the electrons are being generated and where they're being consumed. Balance each half reaction with respect to mass. That means the number of atoms. Balance each half reaction in response to charge. So to make sure that you can see where electrons are being generated and consumed. And then make the number of electrons in both half reactions equal by multiplying the least common denominator between them. So, and this is just, that's the least common denominator. It's like the prime numbers factorization, right? So if you remember that stuff from grade school. So add these reactions together and verify it's balanced. And now how do we do this in acid? So that the previous one is just if you're not in acid. For metals in acidic solution, same steps. Assign oxidation states, do the half reaction, balance each half reaction with respect to mass. So balance everything other than hydrogen and oxygen. Balance oxygen by adding water, and then counterbalance the the hydrogen by adding H plus. And it's easy to use H plus and H3O plus. I know we learned that H3O plus is better, but for me personally, I think this is just a lot easier. And if you have to at the end, then add H3O plus and then rebalance it with the waters. So I'm going to jump ahead, and the next step then, if you're going to do a basic solution, you neutralize the hydrogen by adding OH, and then you subtract the waters. So that's how you do things in a basic solution, is just add that step there. But acid is actually easier. And the last one is balance half reaction by adding electrons. Then you do the lowest common denominator between each of the half reactions, add them together, and then make sure everything is balanced, and make sure and get rid of, like, if you have too many waters on one side or the other, for instance. So let's do this for this reaction here. Iodide plus dichromate makes chromium plus 3 plus iodine solid. So first thing we do is do oxidation states. So easy one is iodine because it's a metal. So also iodine, anion, -1 charge. Then look at the dichromate. So you have to use -2 equals 2 times chromium oxidation state plus 7 times oxygen. So oxygen tends to be -2, so -2 is 2 times chromium plus 7 times -2. So 7 times -2 is -14, so you add 14 to the both sides. So then you get 12 equals 2 times chromium. Divide both sides by 2, chromium is +6. So that's the math you go through, and chromium is +6 on that one. And then chromium on the right, on the +3, is just the charge. So you can see iodide is being oxidized, chromium is being reduced in the dichromate. So now we have these. Now we have to balance them with respect to mass, and so we have to have 2 iodides to form iodine. So that's the first one, and then for the dichromate. Well, first of all, there's 2 chromiums in dichromate, the Cr2O7 -2, and then you need 2 chromiums on the right then. And there are 7 oxygens in dichromate, so you need 7 waters on the right. And now the 7 times 2 for the hydrogens and the waters, you need 14 hydrogen ions on the left. So now you've balanced that. And now, so for 2 iodides, form an iodine, this is going to generate 2 electrons. And the dichromate going to 2 chromiums, it requires 6 electrons. So look at these electrons here. From that, you need to multiply the iodine reaction by 3. So that way you're going to generate 6 electrons that the dichromate consumes. And the lowest common denominator between 2 and 6 is 6. So you just need to multiply the top one by 3. And now you add them together. So you add them together and you can check to see, okay, we have everything, the right number of atoms on both sides. So this equation is in fact balanced, and now you're done. Now, if you wanted to do this in base, if this was in a basic solution, you would add 14 OH minuses on both sides, and then that will turn the 14 H plus into 14 waters. And on the right, you'll have 14 OH minuses. I'm sorry, it'll be 14 waters on the left, and then there will be 14 OH minuses on the right. But now you have to subtract 7 waters from both sides to get 7 waters on the left, and then no waters on the right. But then also on the right will be an extra 14 OH minuses. So that's how you would do it in an alkaline solution. So as I tried to illustrate there, it's the same procedure, but you just you neutralize with the OH minus. So that's done after you balance it first with the acidic solution, then you neutralize it. So it's the same one. So let's talk about a very important chemical reaction, photosynthesis. Photosynthesis, so plants do that. Actually, we do a little photosynthesis too, although we're not as complicated as plants. Plants do it a lot more significantly. We do photosynthesis. We take cholesterol and turn it to calciferol, which is provitamin D. And but plant life takes light from the sun, and then can take carbon dioxide from the air and water, and it can change the carbon dioxide and water into sugar and oxygen. And that's the source of oxygen in the atmosphere, is from plant life. And so ultimately all the stuff comes from sunlight and all the sugar for that. And all of these terms, and then the energy captured, transferred, everything uses oxidation reduction. So we need the sugars that the plants make. We also need the oxygen that they produce. So we are very reliant on plant life. So in the human body, so we burn glucose in our mitochondria to form 6 water, 6 carbon dioxide plus energy, and typically this energy is then used to generate adenosine triphosphate, ATP. So photosynthesis, though, is the opposite. It takes carbon dioxide from the air and water, and then by using photon energy, it turns it into glucose and oxygen. So it's the plants make their own food. So hooray for plants, because we eat the plants. And also we eat the animals that eat the plants. So, oops, I'm using the wrong way. So this is a key process. Photosynthesis is essentially the reduction of carbon. So, and for respiration, though, we oxidize carbon, and that's how we personally, we get most of our energy. We can also do some fermentation, but we get most of it from oxidation. So if we don't have oxidation reduction, we could not have life on Earth. So now let's talk about predicting of spontaneity. So think about a spontaneous person. A spontaneous person just does things. So that's a spontaneous person. A non-spontaneous person is someone you need to cajole into doing something. So same thing with chemical reactions. Spontaneous reactions just happen, whereas non-spontaneous people need to have a little more, incentive. And you can make non-spontaneous processes or reactions happen, but you usually have to pay an energy tax when you do that. So, and we'll talk about this in terms of metals. So people are a little more unpredictable, but metals, on the other hand, are very predictable. And the ones on the bottom of the chart tend to be the lowest to lose electrons, and they're the least reactive. And the ones at the top are the easiest to react. So we're going to show the activity series of reactions, and it shows the elements at the top are more likely to go in the form or the reaction, which means they're more likely to be oxidized. And the half reactions at the bottom are more likely to go in the reverse direction, meaning the ions are more likely to be reduced. So I'll show you the list here. So lithium is the most active of all the elements, and it's the most likely to be oxidized. Look at the bottom, gold. Gold is the most likely one to be reduced. So gold does not typically oxidize, but gold ion, though, is extremely reactive. So you think good old steady gold is not reactive, but you rip the electrons off of gold and suddenly it's a very angry metal and it wants to react with everything. So, and the higher you are up on this list, the more reactive you are, at least in terms of oxidation. The lower you are on the list, the more active you are in terms of reduction. And notice we have hydrogen there in the middle. One thing about hydrogen is also in bold. The metals above hydrogen will corrode in the presence of acid. The metals below it will not. Well, the exception being nitric acid. So nitric acid will react with some of those in there. Nitric acid will not react with gold. So you actually need to get gold to dissolve. You need to add. You have to have something called aqua regia, which is a mixture of hydrochloric acid and nitric acid. This list is incomplete. So platinum, for instance, is also on there, and it won't react with nitric acid either. And many other noble metals, they're down there. But this is just a general list here. So if you want to find a more complete list, you can look at it in like the Handbook of Chemistry and Physics, for instance. So I already mentioned gold. Gold is the top list tend to lose electrons. The ones on the bottom have the lowest tendency to lose electrons. And we use these metals for things that we don't want to corrode, like jewelry, or just things that we don't want to react. So, and that's why we use it for jewelry, because we usually use jewelry as like a indication of a gift or a promise, right? So if you give someone a piece of jewelry and then a few years later it's corroded into nothing, you're like, well, gee, well, thanks for the gift. So we always thought gold was magic because that doesn't rust. It doesn't corrode. So we as humans have always liked gold, thought it was magic. So, but it's not magic; it's chemistry. So, but let's use this here. So, determine whether the following reaction will be spontaneous. So, magnesium metal and with copper forming magnesium ion and copper metal. So, if you look at this, look at the relative position, and let me go up. So remember, it's magnesium and copper, and it's magnesium metal. So look at the list here. Magnesium is the fifth one down from the top. So magnesium is very reactive. And then copper is the third one down from the bottom. It's going to be much more likely. So copper is not going to give away its electrons. It's going to grab electrons. But you look at it, magnesium is up higher. Since magnesium is the metal and it's higher than that, it's more likely to be oxidized. This, in fact, will be spontaneous, and as written, so this forward reaction will be spontaneous by the relative positions of magnesium metal versus copper ion. And remember copper ion because it's the ion, it's not the metal. So in the reactant side of the reaction. So and this, in fact, is spontaneous. So if we were to put magnesium in a copper solution, and copper solutions are very beautiful, nice and blue. So this will react and it'll form copper metal over the magnesium anode there. So if you look at here, will this reaction be spontaneous? So same idea if you look at it. And but if you notice though, iron is below magnesium on the chart, which means that in this case though, since iron is below magnesium, this is not going to be spontaneous. So if you look at the previous example, so copper metal was below the magnesium metal. In this case now though, we have magnesium ion. So it's the opposite part where it's the magnesium ion is testing its ability to absorb electrons to be the oxidizing agent, to be reduced. And magnesium is not a very good oxidizing agent. It will not corrode iron. So this one here, you will not see any reaction. So as mentioned before, most acids dissolve metals. But there are certain metals that don't react, and those are the expensive ones. So copper, silver, gold, mercury, platinum, palladium, and so on. I mean, of course, in this class, we only mention copper, silver, gold. And reaction, though, is nitric acid, because there's a different one. It'll form nitrogen monoxide and bring out this brown gas if you do that. So it'll dissolve copper and silver, for instance. So will zinc metal dissolve in hydrochloric acid? Yes, it will. It's above the hydrogen line in bold. So zinc will in fact dissolve. And so here you can see this reaction here, and this is the way the reaction will progress. So zinc will in fact react with two acids to form zinc plus 2 and hydrogen gas in a gas evolution reaction. So let's talk about, why do we care? Why are we learning this? Well, one of the common applications of this is batteries. So we've used batteries. Although I have my laptop plugged in, if I unplug it, it will be running off of a battery. I carry lots and lots of batteries with me in my cell phone that I carry with me. Heck, I use a battery to start my car if I want to drive away somewhere. So we have lots of batteries, and batteries, they store current. They store electromotive force. And where does the electromotive force comes from? It comes from the electrons. Via a chemical reaction, the electrons are generated. And as the electrons move, we use them to do work. So a common way we do this is using a voltaic cell or a galvanic cell. So these voltaic cell or galvanic cell means the same thing. And we're going to look at one where you put zinc in a zinc plus 2 solution to form a half cell, and a copper strip of copper in a copper plus 2 solution to form a half cell. And if you do this, and we also need to put a salt bridge so in between them, and that's to make sure that ions transfer. And in this case, if you look at the activity series of metals, zinc is more active than the copper, and with that, then the electrons flow. The electrons will flow from zinc to the cathode, and when I always think of it as I do anode corrodes. So the zinc is the anode corrodes, zinc is the one that corrodes, and the cathode grows. So over time, the cathode will get thicker, and the anode will start to dissolve away. And then eventually get to a point where the battery will stop working, and it's usually when the anode corrodes. That's the most typical thing. What happens when batteries die is that happens. But it really it depends on the battery. Though you could run out of copper solution or copper ions in solution, for instance. But typically, when batteries die, it's when the anode corrodes away. And something to note with this: the amount of energy that comes from each of these electrons, it's an intrinsic property. Intrinsic meaning it doesn't matter about the amount. It's like density. So if we took if we had two Olympic-sized swimming pools of next to each other, and we put like a SUV-sized hunk of zinc in one, an SUV size of copper in the other, and then we filled up the pools with a 1 molar solution of zinc plus 2 ions and copper plus 2 ions in the copper one. And then we made this huge salt bridge across them. And then I took a wire from both of the SUV-sized metals, and I was really excited, expecting to see lightning bolts coming from this thing. And if I hooked up to a voltmeter, it would give the exact same number as if it was just a small test tube here, like a beaker on the tabletop. So the electromotive force is the same. So some other terms: the anode is a source of negative charge, and the cathode is a source of positive charge. If you study circuit diagrams, we always say the battery, the positive charge is one that flows, and the positive charge flows. The current flows towards the negative. And what that was is that when Ben Franklin, he's the one that did all the stuff, he had to pick which charge moved, and he picked the positive charge, and he picked wrong. And we know it's wrong. We know it's the electrons, the negative charge is the one that moves. And have we changed everything? Nah, of course not. Why would we change things? We're humans. Once we decide something, we stick with it, even though we know it's wrong. But we're not doing too many circuit diagrams in this class. But it's kind of funny, in chemistry class, you learn that the electrons, the negative electrons, are the ones that moves, and if you go study physics, they'll tell you the positive charges move. We know it's the negative charges move, but we built up all our equations and whatnot with the positive charges moving, so we're just going to stick with that because we're stubborn. So the two half reactions here, and the half reactions are zinc going to zinc ion, and then copper ion going to copper metal by absorbing electrons. But rather than when we do this reaction, though, as the electrons flow, as the current flows through the wire, we can use that current to do work. And then, now we have it in the picture we showed it lighting up a light bulb, but it can be like running a car or running a cell phone or running something else. So, and there is, the voltage. So what is voltage? Voltage it's joules per coulomb is the unit, and coulomb is the amount of charge. So think of the current as the number of electrons flowing. Think of it like water. So how much water is flowing is the current, and how much energy the water has. So you can have a very slowly moving stream, or you can have some really ripping rapids that will just, you jump in there and it'll just take you going. So the really slow moving, that would be a low voltage. The really very powerful rapids would be high voltage. So, and the voltage is the oomph behind it. How much power well, I shouldn't say power, how much energy, power is energy divided by time, but how much energy each of the electrons has as it moves. The higher the voltage, the higher potential. So, and that's what it shows here. And think of it shows a waterfall. I like to think rapids because you can step into rapids, but you step into a waterfall, you're going down. You're going down the waterfall. So maybe if that makes you feel better, if you think of high voltage, think of a really big waterfall. And think of a low voltage, think of a little dinky waterfall. So non-spontaneous reactions do not produce a current. You have to have a spontaneous reaction. Non-spontaneous reactions are good, though, because you can have certain things we'll talk about later, rechargeable batteries. So, but you can have things which have two relatively high. So if the oxidation potential is very high and the reduction potential of the cathode is high, then you will have a very powerful battery. But I should also mention there's other ways to make powerful batteries. You can put them in series, for instance, that then the voltages will add. So if the activity of the metals are really close to each other, then you're going to get a relatively low voltage. But if you have something that's really high on it, you will, like a big difference, will have a very relatively high voltage. And you can really, but these are still kind of relatively low. You're not going to, by using raw elements, you're not going to get a battery with a higher than, say, 6 volts coming from it. To get the higher ones, you have to use tricks like putting them in series. So what's a dead battery? There's a couple ways the battery will die. I mentioned before, the most common is the anode corrodes. So an anode can corrode away. You can also deplete the ions. There's other things. If the salt bridge is taken out, the battery's not necessarily dead, but it's just not going to work because the current's not going to flow. But there are certain ways you can stop the reaction from happening. Right, and of course, not having the salt bridge, it's kind of like flipping a switch, if you will. And also, if there's no electrical connection, if you take the electrical connection between the two metals in the battery, it's not going to go. So, generally speaking, batteries do not expel their charge until they're put into a circuit. Right, you kind of know that. So, you need to have a place for the current to flow. And so, aforementioned, so. The reactants become depleted, and like I said, it's usually the anode is the one that usually depletes. So here's dry cell batteries. Although we tend to use alkaline batteries, and alkaline batteries are similar to this, except that they use potassium hydroxide inside of them. But in a dry cell battery, you have zinc, a zinc in the inside of the battery, and that's the anode. And the cathode reaction is you have magnesium oxide, so magnesium 4 oxide forming plus ammonium to form. So that would be magnesium 3 oxide plus 2 ammonia plus water. So, and typically in these cases, and when the batteries die, it's usually the zinc. So, the zinc is usually the anode, and that's the one that dies. So, and this one produces a voltage of about 1.5 volts. So, but you can put these in series, and you get higher voltages. So if you put them in series, don't put them in parallel, then they don't add their voltages. But if you put them in series, meaning one after the other, you can get it. The potentials add and across them. So for a lead acid volt, so a car battery, these have car battery typically has 6 cells, each of 2 volts each, and they're all in series. And on them, the lead acid, it's 30% or more sulfuric acid in there, H2SO4. You have the cathode and the anode. And this is an interesting battery. Lead acid batteries are interesting because the anode is lead metal, and then the cathode is lead oxide. So if you were, and I don't recommend you do this, and actually, honestly, I never have, but if you take apart a lead acid battery, and if it's charged, you will see kind of a metal mesh that has like a dull gray spongy thing, and then a white kind of powdery thing on the other side, and the white powdery thing, that's the lead oxide, and then that's the cathode, and then the silver, dull silver thing, that's the lead metal, that's the anode. And what's kind of interesting about this is that both the anode and the cathode corrode in this battery, right? They go into solution to form lead sulfate on both sides. And what's nice about this reaction is you can take the car, and if you put electromotive force back on it, the battery will recharge. So lead acid batteries are rechargeable, and then the car's alternator, I mean, you just need the lead acid battery to start the car. And once the car is going, then the alternator takes over as the primary electrical source, and then that will recharge the battery. So be very careful. Be very careful with lead acid batteries, and if you get too much of this lead sulfide or lead sulfate, then it'll stop working. But you need as long as you keep batteries tend to last a while, as long as you keep enough electrolytes in there, like water in there, and as long as it doesn't sit too long, it usually lasts for a while. I mean, in terms of years, right? So it depends on the battery. So we can recharge the battery, and when you recharge the battery, you convert the lead sulfide back into lead metal and lead oxide, also sulfuric acid. So it generates the nasty stuff too, right? So be careful with that. In a fuel cell, I told you we come back to the fuel cell here. If they don't run a gasoline, what are they going to do? Well, the same thing is that you use hydrogen, and there's oxygen in the air, so we need to use hydrogen storage. And one of the problems with this is hydrogen it's dangerous. It's very explosive. It's hard to store. Hydrogen can actually reduce metals and make a type of corrosion called hydrogen embrittlement. So one of the problems about fuel cell cars versus like gasoline cars is that gasoline is just more stable. It tends not to explode as much as hydrogen. So as we go more to more hydrogen fuel cell cars, be careful about getting in accidents with them. They're gonna be more dangerous than the good old gasoline. But I mean, they're very efficient. That's the thing is they're very efficient. So it's a give and take with that. I mean, gasoline is probably more safe than hydrogen fuel cell. But we'll see. We'll see this technology comes. It's still a pretty expensive technology, and it has to do with the difficulty of transporting the hydrogen across the protons, the H+, transferring the protons across to the oxygen to form the water. So here's an image with that, and this is an old image. And actually the fuel cells look like this in the Apollo space program. They're big and huge, and they started to use them quite a bit in the Apollo space program because this is how the astronauts got water. It takes 4 days to fly from the Earth to the Moon, in the Apollo spacecraft. So that's a crazy job there, being an astronaut. You're put on a slow burning bomb called a rocket to rip you off into space, and then the whole time you're gonna have to wait to drink water because it's very weight dependent until the fuel cell generates enough water. So those guys have some courage that I don't have. But this is essentially it's similar. The stuff we do now, we tend to use nanoparticles rather than strips of things, and the anode and cathode, they're both platinum, and the platinum, of course, is expensive, so we tend to use less material from them. Otherwise, I mean, you have to have a budget like NASA to have a car, but they're still not cheap. So we can also do electrolysis, and we can use electrolysis. We use current to drive a non-spontaneous oxidation reduction reaction. And the cell that we use is called electrolytic cell, and the most obvious application for this is nuclear subs. So we can generate hydrogen from oxygen. We Where we typically get hydrogen from is a process called steam reformation of natural gas. So you take natural gas, methane, and you react it with water to form hydrogen and carbon monoxide or carbon dioxide. So it depends on you can form hydrogen in both those reactions, and it depends on if you want to have carbon monoxide or carbon dioxide or however it comes out. So you can tweak the chemical reaction. That's generally speaking how we get hydrogen. We can also get hydrogen by reforming hydrocarbons in distillation columns for fuels. And when you cyclize carbons, hydrogen pops off. So that's the other source of hydrogen that we get typically in industry. You can do it with water. So you can crack water and to make hydrogen. Although we don't typically do this now, it would be a good use for application things like wind energy. Wind energy is not really useful, but you could use it to crack water to generate hydrogen. But part of the problem also is that the oxygen, most of the energy goes into making the oxygen. So by mass, it's a lot more. There's a lot more oxygen than hydrogen in water. But what we really use electrolysis for, and probably don't talk about this in the book, we use it to have sailors breathe on nuclear subs. So the nuclear subs, they when the submarines are submersed for a long time, well, the people still need to breathe. So what do? We crack water and then we dump the hydrogen and we give the oxygen for the sailors to breathe. So that's where we really use this. And so this is our dream right now. And the question is it cost effective versus getting the hydrogen from things like methane? So we don't know. I mean, right now the answer is no, but for the future, who knows? So electrolysis of water, you can see right there. And of course, when you do this, the hydrogen volume is going to be twice that of oxygen. But like I said, we typically use this for things like getting sailors breathable air underneath the ocean. So other applications of electrolysis is that we can add metals. Well, first of all, we can produce certain metals. So this is how we make things like sodium metal, and so you can take something like sodium chloride salt, and you can melt it, and then you can do electrolysis. And on one end you'll get the sodium, and the other end you'll get chlorine gas. And now that's essentially how we make sodium metal and all the other metals, like potassium metal, rubidium metal, cesium metal, for instance, just like that. And you can also use electrolysis to plate noble metals onto other metals. So when you see things like chrome plated on metals on really shiny chrome plated materials on cars and trucks. So showing this for silver. So silver is a relatively expensive metal, but you can coat it, and it can be other metals too. It can be things like nickel, chromium, silver, and gold. All these things you can do, and for cars, we typically coat a thicker layer of nickel and then put a chromium level layer on top of that. But silver, you can plate things in silver. You can plate things in gold, and you just have to be careful because where you put the wire on it is where it's not going to be, when you have to have it connected with a wire, that where the wire is there's not going to be, that's a spot where it's not going to have the noble metal on there. And so you can take a solution and you can put hunks of well, in this case it would be the anode, but I mean it's usually the cathode. But you can take a big hunk of silver and put it in the container, and then you can turn on the electrolytic cell, and then the silver ions will then go and then coat the whatever less reactive metal that you want to have on there. So, for instance, if you want to coat your ring in silver, you put your ring in there and then connect it with a wire, and then put a silver, in this case anode, and put the electromotive force, and then the silver ions will deposit on that less reactive metal. And one of the things, though, if you think about these reactions, you have to be careful what you make your container out of. Also, your wires. Make sure your wires do not have any holes in them, otherwise the wires will start to have silver growing on them. So make sure that there's the nylon container over the ions. Some of these places still use wood, so like wooden beams to submerge whatever it is you want to plate. Plastic is also often used. You can use plastic in this. The bins are oftentimes plastic. You do not want to use a metal bin because then you will just get metals growing on the bin. So if you are going to open up your electroplating business, you got to be careful with your materials. And I think it's kind of funny that they still, we don't typically use wood for many things, but they do use wood frequently for these applications because the wood is not going to have silver or whatever metal it is going to coat on there. And not all redox reactions are great. We've been singing the praise of redox reaction, but corrosion is an example of a bad one. And the most common kind of corrosion is rusting of iron. And so in this case, we show iron hydroxide. It can also be iron oxide. So it's there's a couple of reactions that happen. You can have iron plus 2 hydroxide, iron plus 2 oxide, iron plus 3 hydroxide, and iron plus 3 oxide. So all of these. So, but it's oxidized, and it's by water. So by air. So oxygen. So the iron is the reducing agent, and oxygen is the oxidizer. And this also has to happen in solution. So if you might notice that iron doesn't rust unless it's wet. So you do need to have water with this. So the thing about iron oxide is it's flaky. It's flaky and brown, and it's not as strong as the iron. So that's the danger that we have with this. And it can crumble, and then exposes more iron, and you can corrode things. Really thick iron things can corrode in the elements, and it corrodes down. So in the right conditions, an entire piece of iron can rust away, and if you haven't noticed, it's usually when it happens when it's wet. So iron is not the only metal that undergoes oxidation, but is kind of the more dramatic one for us. And iron is a reactive metal, but it's not particularly reactive. Copper can oxidize too, but aluminum is a very reactive metal, but we think of it as not very reactive. And the reason is because especially aluminum, the oxide is really strong. The oxide is sapphire. It's aluminum oxide is sapphire, and it's a very tough material. It's 9 on the Mohs hardness scale. So, and it forms what we call a passivative layer. So it pacifies the aluminum. Other metals do this. Titanium is a very reactive metal, but it forms a passivated layer. Aluminum oxide, though, it's easily penetrated by chloride anion, so we tend, depending on the application, if there's going to be chlorine around, you tend not to use aluminum. That's why we don't use aluminum in water pipes or ocean-going vessels, but we can use it in freshwater canoes. So you'll see freshwater aluminum canoes, but you won't see aluminum being used for water pipes or ocean vessels. So one of the things, so the coating and this thick passivated layer for aluminum and other metals like titanium, you can do this artificially if you put thick layers around iron. You can protect iron that way. Like the Golden Gate Bridge, that's made a lot of iron, and they paint it. They paint it to make sure that it keep it from corrosion. So that's one thing as a coating. So paint keeps that, but then water happens. So one thing, don't scratch that paint because then you can start to rust. And then if you see the image here, rust is flaky. I mean, you can I can't destroy a piece of iron with my fingernail, but I can certainly destroy a piece of rust with my fingernail. So it'll make the iron much less robust. So what's another way we can do this is we can do what's called a sacrificial anode. So the anode that's higher in activity can be used, and then the sacrificial anode will be oxidized first. And then as long as it's oxidized first, it'll protect the iron. And this is commonly done with iron. We can coat it with zinc, and this is known as galvanization. So a lot of times nails are galvanized, a lot of iron can be galvanized, and this makes it a lot more durable, at least in terms of corrosion resistance. And also for big pieces of iron, like pipes that carry petroleum or natural gas, they'll stick big slugs of zinc, and they'll connect it to the iron, and then periodically every couple of years they will replace the sacrificial anodes to keep the big pipelines from rusting. So that's another way we can do this. So let's go back to the fuel cells and talk about another application of fuel cells. This is used for breathalyzers. So the fuel cell breathalyzer, it looks at the ethyl alcohol, and it does using in an alkaline solution, it can form acetic acid and generates electrons. And then the cathode is oxygen, then replenishing to form more of the hydroxides. So, and the amount of current produced from the breath of the I want to say the patient, the suspect, it's calibrated to figure out how much alcohol is in the person's system, and this is still an indicator. I've never been arrested for drunk driving or have had a breathalyzer used on me. But I think the police have to go and then verify it with a blood test. So, but I'm not sure on that. I'm not a lawyer, but I know that they do calibrate this for a suspected intoxicated driver. So here's an image of that, and then you can see the exhaled breath has the ethanol going in, and then the reaction happens, and then you can do this and figure out what the blood alcohol level is of the suspected drunk driver. So review of this: oxidation reduction. Oxidation is loss of electrons. Reduction is a gain of electrons. And then oxidation states, we have a hierarchy of how to figure this out. Although it does say it's fictitious here, that's not entirely true. There are different chemical properties for different atoms in different oxidation states, but it is a way to keep track of things. So we have activity series as well. So it depends on where you are in the activity series. If you're near the top of it, the metals are more likely to be oxidized. The ones that are lower in the list tend not to be oxidized, but are also, their ions tend to be reduced. So and we talked about that quite a bit. Batteries, we have spontaneous oxidation reduction reactions, and then the anode is the source of negative charge. The anode corrodes, and then the electrons flow from the anode to the cathode, where the cathode then has a chemical reaction such that the electrons are transferred. And for simple metal ones, the cathode grows, but it depends on the chemical reaction. You can just have a reduction reaction happen at the cathode. So electrolysis, we can do non-spontaneous chemical reactions. We'll put the electromotive force in the opposite direction, and then we can do things like crack water or add noble metals to other non-reactive metals in a non-spontaneous reaction. And then corrosion, this is an unwanted chemical reaction, and specifically with iron. And so how can we prevent it? Drain the swamp, meaning keep the metal dry, sealing it with a protective coating, or doing a sacrificial anode. So there's a couple ways we can do that. Here are the learning objectives. And here is the copyright part of it. And Thank you for your time.